Okay, so I think we can start. So welcome everybody to this first session of the Automatica 2020 conference. So this is the scientific session optimization. I'm Diego Regruto, Associate Professor at Politecnico di Torino, and I'm chairing this session. So the first talk today is titled Enhancing Semidefinite Relaxation for Boolean Quadratic Optimization. And the speaker is Sophie Fosson, which is Assistant Professor at Politecnico di Torino. So please, Sophie, the floor is yours. You can start. Il microfono, the microphone is not activated. Okay.
Okay, this was activated. Okay, so thank you very much. So I am Sophie Fosson, and welcome to all to this session. The work that I present to today is a joint work with Vito Cerone and Diego Regruto, which is the chair of the session. The topic of the talk is enhancing semidefinite relaxation for Boolean quadratic optimization. And this is, let's say, a part of the work that we have presented at the IFAC World Congress on July. So a brief outline of my talk. I will motivate and to introduce the problem, the Boolean quadratic optimization problem. I will explain why this problem is connected to, let's say, a rank reduction problem. And then we will see which is our approach to this problem. And we will give some theoretical and some numerical results. And finally, we will draw some conclusions. So first of all, I believe that everyone knows what is Boolean quadratic optimization, but just to be clear on the topic, we mean by Boolean quadratic optimization those minimization problems which have a quadratic cost functional and binary variables. So this is a typical hybrid problems in which we have, let's say, a continuous quadratic cost functional and discrete variables. This kind of problem is ubiquitous in applications. Here I just mentioned a few possible applications like max cut problems in graphs, in operation research we have knapsack problems, for instance. We have such kind of hybrid models in model predictive control, but also sensor selection, medical imaging, compressed sensing, and many others. So let's say that Boolean quadratic optimization is strongly motivated, the study of this topic is strongly motivated by applications. From a mathematical viewpoint, this problem is really challenging. So I give some technical details. First of all, in the talk, I will call Sn the space of n by n symmetric matrices. And to be precise, we will consider quadratic problems of this kind. So we have a quadratic cost functional that we want to minimize over binary variables. For us, binary means 0, 1 in this topic. And let's say we can have also possibly some linear constraint in this problem. For simplicity, in this talk, we will assume to know the sparsity k of the solution. That is, we know how many xi are equal to 1. This is, let's say, an assumption that is quite usual, for instance, in compressed sensing or sensor selection. In our work, we work also in the case where k is not known, but here for simplicity, I show the results when k is known. So let's say we know we have this additive equation, but I mean, if not specified differently, we assume that this linear equation is included in the constraint ax equal to b. Moreover, as in the work by Lasserre in 2016, we will consider, we will consider the relaxed version. That is, the constraint is put into the cost functional by adding a regularization quadratic term with a mu. This mu, of course, is a design parameter larger than 0. Under these assumptions, this problem can be, let's say, homogenized. I mean, I just add the slack variable x0 equal to 1. And in this way, we can rewrite the problem as an homogeneous problem. So in the rest of the talk, I will consider this problem, xtqx, where q can be a matrix that can be computed quite easily from this. Okay, so given the problem, well, of course, this problem is NP hard because, okay, the cost functional is quadratic, but let's say that we have binary variables, so this is inherently NP hard. But in the literature, there are some approaches to solve this, to try to solve this difficult problem, and typically one uses semi-definite relaxations. So in a nutshell, semi-definite relaxations means the following. First of all, let me call Sn plus the subspace of positive semi-definite matrices with the usual Frobenius inner product, which correspond to the trace of the product of two matrices. And so we transform, let's say we relax the problem from xtqx, the minimization of xtqx, to, let's say, q by x in a, let's say, Frobenius inner product, where the relaxation is from the fact that instead of considering the matrix x by xt x vector, we consider a generic positive semi-definite matrix. So, of course, this matrix has rank equal to 1, of course, while here we relax to any x, which is positive semi-definite. And so we can rewrite the problem as a semi-definite programming problem. And of course, this kind of problem can be solved, and it's convex, no problems. To be careful, we have to pay attention to this constraint that we have added. So in particular, we added the constraint that the diagonal of this generic x, matrix x, must be equal to the first row. This represents the fact that we know that the variables must be 0 or 1. Then we know that each xi is equal to the square. And so we can add this information because, let's say, we somehow we expect, we want that, let's say, in this generic x, we have this kind of structure which is typical of the matrix, let's say, the original matrix x by xt. Okay, so in this way we have, let's say, a relaxation. Of course, we are not sure to get the right solution, but we have some possibility to get the right solution. In particular, as I've said, the problem now here is to find, let's say, the solution with rank equal to 1. Because if we find the solution with rank equal to 1, according to some results, we are sure that we have extracted the right solution. So we find actually the matrix x by xt, from which we can extract the correct binary solution. So let's say that we want to try to, let's say, support or induce this minimal rank, or at least to try to, to reduce it. This, of course, has been studied in the literature. Mainly, we have two kinds of approaches. The classical one is the convex approach, according to which it is suggested to minimize the nuclear norm. The nuclear norm is, let's say, the convex envelope of the rank of a matrix. So if we minimize the nuclear norm, we have some hope to, let's say, minimize the rank of the matrix. Of course, this is an heuristic, but it works pretty much well in many cases. For us, it's not true because if you remember at the beginning, we have said that we know the sparsity of the initial of the true vector. And so in particular, the trace of our matrix is somehow fixed by construction, because it depends on the sparsity. And so minimizing the nuclear norm has no effect in this case. Other possible approaches, well, we have the non-convex approach. Of course, I will not enter into detail of why this works, but if you minimize the log det of a matrix plus this, well, this is just a small epsilon to avoid the numerical problem. Also, in this case, you get the effect of reducing the rank of the matrix. And this non-convex approach proposed by Fasel in 2003 is very effective, but it is non-convex, and it let's say it involves the use of an iterative algorithm, which requires the n-dimensional matrix inversion of at each iteration. So it is quite computationally intense. Okay, let's go on and explain our approach to this problem. So also our approach is a non-convex approach, but different from that of Fasel. In particular, so let me call X star the desired one-rank solution to the semi-definite relaxation that we had presented before. Then we know that the eigenvalue vector of X star has this shape. So all the eigenvalues are equal to 0 except for one, which is larger than 0. But we have an additive information. Since we know that the trace is equal to k plus 1, where k is the sparsity of the original vector that we assume to know, then, of course, also the sum of the eigenvalue is equal to k plus 1. And so, in particular, we know that V0 is equal to k plus 1. So we know exactly that the eigenvalues are all equal to 0, except for one, which is equal to k plus 1. So to try to induce this, this shape to the eigenvalue vector, we can just notice that if we have any vector with values between 0 and a, and we know that the sum of the components is exactly equal to a, we can force one sparsity of this vector by minimizing the energy. Because, sorry, by maximizing the energy. Because if we maximize the energy, we somehow concentrate all the mass in a single component. So this is a way to sparsify. So our idea is to try to maximize the energy of the eigenvalue vector. And we can see that the energy of the eigenvalue vector is equal to the product of X star by itself. This new cost functional, of course, here we have a minus because it's a minimization problem, and lambda is some design parameter. So very briefly, the theoretical results is that this kind of problem has a solution, but we have the problem of, let's say, achieving this global minimum. So for the moment, what we proposed is an alternating minimization algorithm. So it is a suboptimal algorithm, but it works pretty much well in the experiment. Okay, so I will not go into details of the algorithm, and let me skip now to numerical results. Okay, so here we consider a numerical experiment. Well, we simply solve, let's say, a compressed sensing problem. Okay, so we have, we start from an equation AX equal to B, which is underdetermined as in the compressed sensing theory. And we know that the solution must be binary. So we relax it. So we actually solved, let's say, quadratic problem. And here, okay, we have some specification. So A in our experiment is random Gaussian. The dimension, okay, the n is equal to 50, and we vary the number of measurement m and the sparsity of the vector. So let's see some result. In this graphs, I show the exact recovery rate over 200 random runs. In this first slide, we have the classical approach. So here we have the classical semi-definite relaxation, the nuclear norm heuristic, and the log-det heuristic. As we have said, there is no difference in this case between SDR and nuclear norm heuristic because in the nuclear norm heuristic, we minimize the trace, but the trace for us is fixed. We can also see that, let's say, with the log-det heuristic, we obtain some enhancement. In particular, well, more or less for all m and k, we obtain some enhancement, but we can see that in particular, when m is larger than 28, with the log-det heuristic, we obtain also 90% of success. Let's see what happens with our approach. Our approach is named with the acronym KBE. So what I have explained in this talk is algorithm 1. Then we have another algorithm that I will not discuss today. But let's say the general message is that with our approach, actually, we have some enhancement. So we improve with respect to the log-det heuristic, which in turn improved with respect to the nuclear norm heuristic. In particular, if we want to see some special point, well, when m is larger than 28, our approach gets at least 96% of such a success. So it's, let's say, a significant improvement with respect to the log-det heuristic. Okay, so just to conclude, in this work, we have presented a novel non-convex quadratic regularization method to improve the solution of semi-definite relaxation for Boolean quadratic optimization. We have some theoretical result about the fact that the problem that we propose is well posed. And we have some heuristic algorithm, some local minimization algorithm that, I mean, could be improved. In our future work, we are trying to improve this algorithm, for instance, by studying some suitable initialization, because of course, at the moment, we have no guarantee that it gets the real global minimum. But in the practice, in numerical experiment, we observe that we obtain an improvement with respect to the state-of-the-art algorithms. So as I've said, future work will be devoted to study how to improve this algorithm. And also we will provide some more refined theoretical analysis of the algorithms. This concludes my talk. If you have any curiosity, you can see our paper at IFAC, and also to visit the website where there is always updated information about our work. Thank you very much.
Okay, thank you, Sophie, for your talk. Okay, now we have time for one or two quick questions. And if you want to ask a question, please use the specific chat, which is called question and answer, or DNR for the Italian version of Zoom. So if you have a question, please write there, and we will allow you to ask your question. Okay, it seems there is no question, so we can move to the second talk. Thank you again, Sophie.
Thank you.
And Nicola, if you can share your slide.
I cannot until.
Okay, maybe. Okay, maybe now. Okay, perfect. So the second talk is about ADMM for robust distributed optimization. Our speaker is Nicola Bastianello. So please, you can start. Thank you.
Thank you. And hi, everybody. So I'm Nicola Bastianello, PhD student at the University of Padova. And I will present this work, which is a joint work with Ruggero Carli and Luca Schenato. So, okay, I will quickly introduce the problem statement, then go through a bit of details about the proposed algorithm, show a couple of convergence results and some numerical results. So first of all, we look at distributed systems in which we have agents with computational capabilities that communicate with each other with the goal of solving a common cooperative task. For example, we can look at sensor networks, mobile robots, smart grids, and any kind of distributed system. The general problem that we look at is as follows. We have a connected and undirected graph with n agents, and we want to minimize the sum of the FIs, which we call local costs, subject to consensus constraints. That is, that the local states xi be consistent among all the nodes that are connected. So, yeah, as I said, we have private local costs, Fi, which we assume to be convex. The nodes can communicate only with a subset of the other nodes, which we call an I. And each node processes local information and shares the results with the other nodes. These kind of distributed systems can pose some interesting challenges. For instance, asynchrony, in which the nodes do not share a common schedule. For example, they have heterogeneous computational powers, so they activate at different times. Or there may be communication failures, so communications between two nodes may not be successful. And in this presentation, I will talk about an ADMM-based approach to solving this problem, this distributed problem, in the presence of both asynchrony and communication failures. All the details are in this paper to appear on TAC. So before I go into details about the proposed algorithm, I want just to point out that asynchrony may be seen as both a challenge, but also as a feature. Indeed, as I was saying, if, for example, we have a network with nodes that have very different computational capabilities, and we have them perform in a synchronous fashion, if we can, then it ends up that nodes with faster computational rates have a lot of idle times, while asynchronous executions do away with all this idle time. So it's a challenge, but also can be an important speed up. Okay, so let's see our proposed approach. As I said, it is based on the alternating direction method of multipliers, which I believe is widely known. I won't go into much detail about it. Let's just say that it is a very simple algorithm with very good performance, and that, as we will show later, and that is very robust. There are two possible formulations of ADMM, a Lagrangian-based one and an operator-theoretical one, which we use. That, just to mention it, is the dual of a Pisman-Rackford splitting. So the first step is to reformulate this problem by changing the consensus constraints into this equivalent form, where we introduce the bridge variables y, I, j, that as you can see, still enforce consistency among the nodes. Thanks to these these constraints reformulation, we can apply the ADMM to the distributed problem and get a distributed ADMM formulation. Okay, so accounting also for asynchrony and communication failures, this is the algorithm that we get. All the details are in the paper that I mentioned. So we have two sets of initial conditions, one for the states and one for these auxiliary variables, of which more later. And we have two parameters, the penalty rho and the relaxation alpha. So the algorithm is as follows. We have a first step in which a node I, if scheduled to activate, performs an update of the local state, in which the information it uses is this set of zij's, which are local information, as well as xi, which is the local state that it's updating, and fi, which is the local cost. I highlighted in blue the fact that this step is conditionally performed on activation of the node I. That is, if node I has completed the previous update, then it will perform a new update. The second step is for the node I to share xi and zij with its neighbors. Of course, as I mentioned in the problem statement, these communications may be lost. Finally, if node I receives new information from its neighbor j, which again it may not happen, then it can go on and update the zij. So I introduced previously the bridge variables, and now I am talking about these auxiliary variables. So basically, the auxiliary variables, we have as many of them as we have bridge variables. So a number equal to the number of neighbors that node I has. And in a Lagrangian-based ADMM, these zij basically are the Lagrange multipliers. We call such ADMM formulation an edge-based formulation because we have that the number of variables scales with the number of neighbors. We can give node-based formulations as well, but they are not as robust as edge-based ones. As I mentioned, we have two free parameters that, differently from gradient-based methods, are chosen from a fixed set. And then, just a note, the xi update is actually a proximal update. Okay, so let's see a couple of convergence results. We work under the assumption that the local costs are convex, the graph is connected, and that activations and communication failures are independent events, both among themselves and over time. Furthermore, we can give a more refined result under the assumption that the local costs are twice continuously differentiable and strongly convex. So, first of all, under the first two assumptions, and for any initial condition of the auxiliary variables, we can see that the local trajectories, the trajectories of the local states, converge almost surely to one solution of the distributed problem. And this is a consequence basically of using the operator theoretical ADMM formulation that we have. So almost surely the nodes reach consensus at an optimal solution of the problem. Further, if we have also that the third assumption holds, then we have the following statement. For any initial set of initial conditions of the zij's that are close enough to the optimal solution, then we can say that in mean, the local trajectories xi converge to the unique optimal solution of the original problem. Unique because we have now strongly convex local costs. This is what is also called R linear convergence. So just as a corollary of these two results, we can say that the proposed method has eventual linear convergence. That is, after a transient of finite length, the algorithm will converge linearly. This is a consequence of the fact that by the first result, we do reach a neighborhood of the optimal solution, but possibly in not with a linear rate. And then afterwards, the second result kicks in, and we can show that the convergence is linear. So just a quick rundown of the proof for the second result. The main idea is that, as we well know, locally around the optimal solution, the costs can be modeled as a quadratic function with a perturbation term that is decaying the closer we get to the optimal solution. As a consequence, ADMM can be seen as a perturbed affine operator. And we know that since we are operating in an asynchronous and lossy network, this affine operator is actually a random affine operator in which coordinates are updated probabilistic with a probability. From operator theory, we know that affine operators do converge linearly, and moreover, this holds as well for random operators. Then we can combine the first result with these main points and get a convergence. Interestingly, since we have an affine operator, we can use it by computing its eigenvalues, we can use it to estimate the convergence rate. Okay, so let's see some numerical results. We have a graph of 25 nodes with the local states of dimension 5, and the costs are quadratic for simplicity. Agent activation and communication failures are modeled as uniform random variables, and we average over 100 iterations. So this first result shows the logarithm of the tracking error.
So, sorry, Nicola, you have two minutes left.
Sure.
Okay, thank you.
And yeah, so we can see the logarithm of the distance from the optimal solution for different packet loss or communication failures probabilities. As we would expect intuitively, the higher the packet loss probability is, this lower the convergence rate, because we are updating less and less over time. An interesting result is this one, in which we have the raw alpha plane, that is the plane of all values that the free parameters can take. And we have these curves which are defined by all the such that all the points below the curve have shown convergence empirically. So the numerical results, sorry, the theoretical results that I mentioned ensure that below 1, all the parameter pairs are fine, lead to convergence. But we can see that we actually have some leeway for low raw parameters. Just to conclude, as I mentioned, we can use the affine operator formulation of our proposed algorithm to estimate the convergence rate. And here we have a plot for the empirical convergence rate. And here we can see the difference with the theoretical convergence rate. So as you can see, it is quite small, with a maximum difference, relative difference of 10 to the minus 5, for instance. And we have, yes, in the empirical convergence results, we have again this fact that the higher the packet loss probability is, the slower the convergence rate. Okay, so this concludes my presentation.
Okay, thank you, Nicola, for your presentation. And so regarding question and answer, I would like to clarify that all people can ask a question through the Q&A chat, while the speakers of the session cannot access such a chat and can ask a question directly by voice. Okay, so we have a first question by Sophie Fosson.
Yeah, can you hear me?
Yes.
Okay, so thank you, Nicola, for a very nice talk. Just a curiosity, so your approach is for, let's say, lossy networks in which you can have some packets that are lost. Just a curiosity, I wonder if the same approach could be used in, let's say, adversarial setting in which the packets are not lost, but there is some, let's say, bad guy in the network that delivers corrupted information, for instance. I mean, just I wondered if you had thought about this, or I mean, it's not, of course, it's not in your work, but something, let's say, that maybe could extend. Just a curiosity if you have thought to this to an adversarial setting, let's say.
So as far as I know, there are some works in which ADMM is shown to be robust to noise on the communications, which I believe is close to what you were
exactly, yeah,
hinting at. I think I haven't seen them, but there is a growing body of research about distributed optimization with, I mean, adversaries or like privacy preserving, in which you want to keep your data away from adversaries. So yeah, I guess there may be something about ADMM as well, but all I know is that it is robust to noise on the communications. That far.
Yeah. Okay. Thank you very much.
Okay, thank you. We have time for one more quick question. Okay, if we don't have any additional question, we can move to the next talk, which is distributed primal decomposition schemes for constraint-coupled optimization, that will be presented by Andrea Camisa. Please, Andrea, if you can share your screen.
Can you see that?
Okay, perfect.
Do you see also this bar here? Or,
yes, also the bar. If you can enlarge full screen, maybe it's better.
Yeah, so
Okay.
Maybe
Thank you.
this way I can.
No, it's fine, I guess.
Okay. Thank you for your introduction. Can I start?
Yes. Yes,
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 maybe,
please.
I didn't start my video. Okay. Can you see me?
Yes, yes, please.
Okay.
You can start. Thank you.
Thank you. Thank you for your introduction. I would like also to acknowledge the ERC project of Opt4Smart, within which this work has been carried out. This is hosted by the University of Bologna and directed by Professor Notarstefano. So my work is about distributed optimization, and we are drawing inspiration in particular from many contexts in which distributed optimization problems naturally arise, and these problems have a different structure with respect to consensus-based optimization, because we have the minimization of a sum of contributions, but these contributions only depend on a local portion of the optimization variable, so they somehow depend on separate portions. And so, as I said, this is different from consensus-based optimization, and they carry some challenges which have to be faced to solve these problems efficiently. And I would like to show you some of these challenges on a practical example. So if you consider n dynamical systems interconnected by a network, and you formulate an optimal control problem for these systems, so you can see here that you have the constraints given by the dynamics of these systems. In this example, they are linear. And you see that this problem has some difficulties, and in particular that the optimization variable is large scale. And indeed, this happens when there are many dynamical systems to be controlled. And also, if the systems are mixed logical dynamical systems or hybrid systems, the constraints in the problem are also mixed integer, which is a serious difficulty in tackling this problem, because this makes the problem non-convex and also NP hard. You can also have time-varying communication network, which also poses another challenge in handling this kind of problems. And we would like to design a framework that takes into account all these challenges together simultaneously. And we have done this, and I will proceed as follows. I will start with a simplified setting with convex problems, but then I show you all the extensions of this framework to handle all the difficulties or the challenges that I showed you in the previous slide. So let's start with this convex optimization scenario. So we consider this constraint-coupled distributed optimization setup. The setup works as follows. You have the minimization of separate contributions of cost function. All of them depend on separate portion of the variable. And these local variables are subject to local constraints. And there is a coupling constraints among all of them. And you can see that this is a condensed problem formulation, because it can embed all the problems that I showed you the previous slides. And we assume that each agent I only knows its own portion of cost function, of constraints, and of coupling constraints. And for the time being, we assume that the cost function and the constraints are convex, but I will show you next how to extend this to the mixed integer case. So to handle this problem, we use typically people use dual decomposition techniques, but we use a different method, which is as follows. We consider the coupling constraints, and we view these coupling constraints as a limited resource that must be shared among all the agents. So ideally, the agents have to fit these total resource with their own contributions to the coupling constraints. But then we assume that this total resource is split with n portions, and each of these portions, which is kind of allocation of the total resource, is assigned to each of the agents. So we consider here the generic agent I. And if we assume that agent I is assigned the resource yi, we can formulate this problem with minimization of the local cost function subject to local constraints, and also this allocation constraint. And the agent I can compute its own portion of solution with this problem. And of course, the solution of this problem depends on the choice of yi. And in this respect, we can define a function which gives the optimal cost of this problem depending on the chosen value of yi. And in general, we can think of this original optimization problem as split into a hierarchical structure, which is, now I sketch. So you have the local subproblems of the type that I just showed you with these functions that are called primal functions. And you formulate the original problem as the minimization of the sum of these primal functions, subject to the constraint that the used resource is equal to the total available resource. And you also have these additional constraints, yi into yi, which model the fact that for certain values of yi, the subproblems may be infeasible. And you want to ensure that the subproblems, of course, are not infeasible. And as I said, this is a hierarchical structure that allows you to reformulate the original problem. You can delete this further constraint here by introducing a relaxation approach that is you can see now in the slide. This is based on an exact penalty approach and allows you to remove this artificial constraint. So with this in mind, we can formulate a distributed optimization algorithm working basically on the master problem. And this works as follows. So you consider the network of agents, and the algorithm interleaves communication and computation. And from the perspective of the node I, this consists of a minimization phase of the problem that I introduced before. When you have your assigned local allocation yi of t, you minimize this, you solve this problem, and you find the Lagrange multiplier of this constraint. After you do this, you update your local allocation using also the information coming from the neighbors, and this updates the allocation and gives you a new yi vector to start with the next iteration. And you repeat this operation, and eventually this converges to the optimal solution. And indeed, we have this theorem which says that if you consider the sequence generated by the distributed algorithm with alpha t diminishing step size and m positive parameter, which must be sufficiently large, then you have cost convergence, and you have also convergence in the sense of every limit point convergence to the optimal solution of the problem. So if, of course, if your optimal solution is unique, this translates into convergence of the whole sequence, but in general is limit points. So this algorithm has some differences with respect to the state of the art, because we don't use rounding averages in our algorithm. And indeed, this translates into some improvements into as for the convergence speed. So here you can see a numerical example on electric vehicle charging. We considered a scheduling problem in which we have 50 electric vehicles that must be charged. And this can be formulated with a kind of optimal control problem with discretized battery dynamics. And we have some coupling constraints given by the power grid. And you see that the plots confirm the theoretical findings, and in particular, if compared with the state of the art, actually this outperforms the state of the art. And also note that, interestingly, this algorithm tries also to saturate the coupling constraints, because intuitively what prevents you from giving a better accuracy with the cost is the fact that you are not utilizing fully your constraints. And this algorithm works pretty well in this respect. So let's go now on. Yes, I forgot to acknowledge the disrupt package developed by our project, and I performed all the simulations of this numerical experiment with this package, which is freely available on GitHub. You can download it if you're interested. So let's go now on, and let's discuss the extensions of this algorithm to the more challenging cases mentioned at the beginning. So in particular, we now consider time-varying networks, and the network model is as follows. We have a given underlying graph, and we assume that each edge has a given activation probability. We only assume that these probabilities are positive, and the network works as follows. At each time instant, we toss a coin, and we see if each edge is active or not. And we repeat this experiment at each time instant, and we see that at each time instant, the active edges can be quite different. We have several combinations, and therefore this communication scenario is very challenging. And to adapt the algorithm to this scenario, it actually only suffices to adapt the update rule by just removing the previous sum and putting another sum all over the currently active neighbors. And this quite simple modification actually involves a lot of different results in the analysis. In particular, to analyze this algorithm, it is necessary to recast that into a block subgradient method, in which the current state of the algorithm is translated into a block variable in which each of the blocks corresponds to an edge of the graph. And when the edge is active, this means that that particular block is being updated. And by analyzing the algorithm in this way, we are able to show this theorem, which says that if you consider the revised distributed algorithm with the same assumptions as in the static case, then almost surely you obtain the same result of the static case, and namely cost convergence and every limit point being optimal solution. And you can see that this is a very powerful result because both in the static case and in the time-varying case, we have basically the same result with the only change given by the activation probability being positive.
So, sorry, Andrea, you have 2 minutes left. Okay.
Okay. So let me now show the extension to the mixed integer case. In the mixed integer case, we have mixed integer constraints locally, which are kind of these stripes with linear cost and linear constraints. If you convexify the local constraints, you obtain a convex problem. And there's a powerful result that we use, which says that the solutions of this problem are already mixed integer for at least n minus s portions. So we only have to adapt the remaining portions. And let me go quickly. So if you consider now the coupling constraints of this case, and if you restrict these constraints by a given restriction, we solve this problem with our distributed algorithm for convex problems. And then we use the allocation given by the distributed algorithm to compute the solution for the mixed integer sets. This may require a given violation, but then in the end, this violation by the previous theorem are at most S. And these are embedded into the restriction sigma, which we designed to be as small as possible. And the distributed algorithm is with the solution of the convex problem with our distributed algorithm for convex problems. And then we use this solution to compute a mixed integer point. And the theorem that we showed is that the solution computed with this algorithm is feasible in finite time. And indeed, we showed that if the number of iterations is large enough, then the solution computed by this algorithm is feasible. And also we can compute suboptimality bounds theoretically. And would like just to show you the power of this algorithm, that in a mixed integer microgrid control problem, we were able to, so this is a very large scale problem with 6,000 optimization variable and 1,000 binary variables. And this has, so you can see that the blue bars are our algorithm and the red bars are the state of the art. The restriction magnitude is 2 orders of magnitude below the state of the art. And also the suboptimality is very low because we only have 3% suboptimality with respect to the optimal solution of the problem. So just to sum up, I'm sorry for going quickly on this second part, but to sum up, we considered constraint-coupled distributed optimization with primal decomposition schemes, and we showed this flexible framework which works both for convex and for mixed integer programming. And this is suited both for large-scale problems and also in time-varying networks, and has applications to many interesting problems such as task assignment, task allocation, and distributed control problems. And with this, I end my presentation. Thank you for your attention.
Okay, thank you, Andrea, also for your effort to speed up the second part. Thank you very much. Okay, we have time for 1 or 2 questions. Okay, maybe there is one. Okay, if you can read, there is a question in the question. Okay.
So, how does your distributed primary composition relates to the solution of the dual Lagrangian problem? So, are you referring to the mixed integer case or the convex case? But then in general, I can say that so of course, if you consider the convex case, since you are solving the problem exactly both with the dual decomposition and with the primal decomposition, you obtain the same solution. What is different is the decomposition technique that we use to solve the problem. And for the mixed integer case, indeed, this has also led to some improvement in the solution, because there's a paper with dual decomposition applied to mixed integer programs, but this may lead to conservative solutions. And our approach indeed improves this kind of solutions. Does this answer?
Okay. Okay. Perfect. Okay.
Thank you.
Okay. Thank you very much. So we have time for another quick question. Okay. Okay, we can go on. The next talk is about asset membership approach to data-driven global optimization. And the speaker should be Lorenzo Sabug. Okay, perfect.
Hello.
Okay, hello, good morning. Okay, so please, you can start. We cannot hear you. You have to switch on the microphone. Okay.
Now?
Perfect. Okay.
Okay, thank you. Thank you so much. So let me switch back to my presentation right now. So good morning, everyone. I am Lorenzo Sabug Jr. and I'm a doctoral candidate in Systems and Control at Politecnico di Milano. So I'm working with Professors Fredy, Ruiz, and Lorenzo Fagiano. So far we have developed a global optimization technique that is applicable for a wide range of applications. For example, when you've had this brand new control strategy and you want to tune its coefficients, because there is not yet any solid relation between your tuning and your performance. Or maybe you want a mobile robot and you want to simultaneously optimize your mechanical specs and your control gains, or any other systems actually, in which there are complex interactions between electromechanics, hydraulics, or pneumatics, and experiments are the only sensible way to evaluate them. So these problems are the main focus of our work, which are generally called black box optimization. So it is called as such because they don't have explicit models or closed form equations to relate the input parameters to the cost function, which makes optimization or tuning a very hard task. So that means in order to see how the system behaves with your mix and match of parameters, you actually have to do the trials or the experiments and to measure the performance yourself. So of course, these experiments can be resource intensive or time consuming. So you better choose your test points strategically to get the best out of your tuning campaign. So in other words, you use information from your previous trials and hopefully you can use your next test point, which is better than your current best. So for this, we have two conflicting goals to improve on our current best data. One is to exploit the position of the best data, as we can see here in this animation. So in the hope that nearby there's a better point, as shown in here. So as we can see, you can only improve so much on your current best point that we might get stuck on a local minimum, as we can see here. And so you want to go to unexplored regions to know if there is still something out there that you might miss and might actually be better than the current best point. So this goal is called the exploration. So in other words, a good global optimization algorithm should find a balance between these two priorities. To introduce the problem that we want to address, we are putting forth, of course, some assumptions first. No? So suppose first we have this black box function f0, which is a scalar function having a domain of dimension d, and we suppose we are searching around a search space curvy x. So the first assumption is that the f0 is Lipschitz continuous, which has a finite but unknown Lipschitz constant gamma naught, this one. The second assumption is that the curvy x has a polytopic geometry, and for this presentation we can just use, without loss of generality, a very simple hypercuboid. And now we are ready to state the problem. So the goal is to design an algorithm that generates a sequence of points x1, x2, x3, and so on, with their associated sample values z1, z2, z3, and so on, such that whenever you require a certain finite optimality tolerance, we can name it epsilon, that algorithm can produce a sample within the tolerance from the absolute best value. So and this best result can be generated within finite iterations. And now to motivate our algorithm, I show first the general concept of set membership identification. Suppose that we have the black box function f0, as we can see here in broken line, and we have sampled it n times. So we are given data points x and the corresponding values z. No, the data are now shown here as black points, and now we have calculated the Lipschitz constant. We can name this gamma n, which is compatible with the data we have so far. We see that given any sample and the Lipschitz constant, we can just geometrically draw a set around the sample, which means the feasible range of values in this unsampled region, which are defined using the upper bound here and the lower bound on the other side. So note that the bounds are calculated solely on the basis of the sample and the slope gamma, and which is quite literally the Lipschitz assumption. So we can get similar sets for the different points, and we can get the resulting intersection of all these sets. So we call this set the feasible functions set, which are characterized by the overall upper bound z bar, and the lower bounds z minus. Furthermore, we can also name an uncertainty lambda, which is simply the difference between the upper bound and the lower bound. So it goes to say that the further you go from any sample, the uncertainty goes larger. So these are the mathematical formulas for the upper bound and the lower bound. Yes. So the bounds are actually the intersection in general of conic sections. And this is how the lower bounds look like for 2D. So as we can imagine, in the next 2D example, the sampling would generate an upward and a downward facing cone for the upper and lower bounds respectively. So when we generate more samples around the search space for Vx, the bounds fit the black box function tighter and tighter. So now we can see that the set membership can quantify the uncertainty as well as the function estimate. And both features are attractive for black box optimization because you want to learn and optimize the function at the same time. But of course, you want to optimize first. And now we present the mechanism of the set membership global optimizer. We can call it SMGO. So it works given a set of samples, and it iteratively chooses the next points for sampling. So priority is given to exploitation, as will be discussed later. So if it makes sense to exploit, then we sample the selected exploitation point. But if not, we can just explore around the search space using the uncertainty measure. For a very simple presentation, we can just show one-dimensional case. So suppose that after iteration n, we are given these three samples. And the exploitation searches the candidate point by somehow crawling down using the lower bound z underline from the current best point, which we call xn star. So your search area is only within the vicinity of the lower bound cone of xn star. Because there you are quite sure you are most probably getting a better point than xn star. So we pick the candidate point with the lowest lower bound, as we can see here. It's obvious, and we check if it's worth to sample that point. So the worthiness is simply measured by the expected improvement of this lower bound compared to the best sample we have so far. If this improvement is large enough, for example, if it exceeds a certain improvement threshold, then we sample it. But otherwise, we should do an exploration. So this is how it looks like in one dimension, but how does it look like in 2 dimensions or higher? So it goes like this. Suppose we have n existing samples after n iterations, and we have identified xn star as the best point. Exploitation means going down the lower bound cone. So ideally, we would like to minimize the lower bound, the z underline, around the vicinity of the xn star. However, this subproblem is not convex because, well, we remember the multiple cones geometry, right? So we'd like to do another computationally efficient alternative. So the thing is this: we draw lines from the xn star to all the other samples, and we collect the candidate points along those lines using the simplified one-dimensional side view geometry, as in the 1D case. And now we pick the candidate point with the lowest lower bounds, and we subject that point to the expected improvement criterion. And so that's for the exploitation part. And now when there is no viable exploitation point, we will directly switch to exploration to pick our next sample point. So this time we pick a point with the maximum uncertainty to learn the shape of our function after sampling. So we are searching for the maximizer point for uncertainty, this one. And we would ideally maximize the uncertainty over all the search points. But now we should realize that this maximizer, this argmax is also a non-convex subproblem. So I think we should propose another simple mechanism. So now we should realize that at least in one dimension, the midpoints between the samples would usually have this highest uncertainty. For example, in this point and in this point. And so we exploit this simple fact. So we pick all the midpoints as candidate points, and we pick the one with maximum uncertainty. And now we take this logic to higher dimensions. So we take some sample points, and now we generate a full mesh out of them. And just for simplicity, we can just acquire all the midpoints of these segments and just pick the candidate point with the highest uncertainty. This selected point will then be sampled for the next iteration. And so this way we can have either upper bounds and lower bounds, which can be used in the next iteration, whether to use an exploitation or exploration. And so a simple summary of the algorithm is shown here. So suppose we have some initial samples, and we can update the Lipschitz estimate gamma n. We find first the exploitation point as discussed earlier and test it using the expected improvement test. But then if it passes, we can just directly sample it and iterate the next one. But then if it fails, we proceed to the exploration point to select the exploration point, and it will be the one which will be sampled instead. For the SMGO algorithm, we have also studied some properties. So such properties I would mention in this presentation. So mainly the convergence of the optimization result and the computational burden. So we have proven that the SMGO somehow produces a dense point sequence, which implies that for every required optimality epsilon, SMGO will produce a best result that fulfills this optimality requirement after finite iterations. And furthermore, in the aspect of computation, we can use an iterative implementation of the algorithm so that we can keep the computations into only a polynomial complexity. So we would like to test the SMGO, of course, comparing it to other state-of-the-art optimizers. So we are comparing it side by side with other optimizers such as ADMM, a direct and the Bayesian optimization, as this is available in just a built-in function in MATLAB. So there were 500 iterations per run of this test, and of course to give a statistical spread of the results we are using, we performed 100 independent runs of the optimization with different starting points. So now we start with the results using the Rosenbrock function, which is shaped like this on the 2 dimensions. So we see that it has a unique minimizer point, which is located here in the 2D. But then we are comparing the algorithms on the 10-dimensional version of the Rosenbrock function. So we note that we first note that direct does not have any spread because it's a completely deterministic method, and it has a fixed set of starting points. So it's the same result after 100 independent runs. Furthermore, the results show that ADMM does not fare very well in this case because of a completely randomized exploitation and exploration. That means it does not fully utilize the function structure within the search space. On the other hand, the SMGO fares very well, even in comparison with the widely used Bayesian optimization. And after 500 iterations, we can see here that some runs had actually much better results, given that this graph is a log scale. And next are the results with Deb's function number 1, which looks like this. And as we can see, it has a very many global minima, which are regularly spaced with each other. So we show the 2D version for visualization.
So, sorry, Lorenzo, you have 2 minutes left.
Okay, sure. Okay, thanks. And now we test it with the 5-dimensional version. The direct algorithm somehow resulted in a worse performance because of the mechanism of direct, which is recursively subdividing the search space into recursive rectangles in the hope of homing in on a minimum point, is not really compatible with the structure of the function. On the other hand, ADMM, Bayesian, and SMGO have displayed similar spread, but with SMGO we can see that in numerous optimization runs, it has already achieved almost the theoretical minimum. On the other hand, regarding the computational time, we can see that in this log scale graph of per iteration computational time, the SMGO can be implemented in the polynomial complexity as predicted in our analysis. So we can see a curved trend in this log graph, which is much faster to the exponential complexity of Bayesian optimization, as we can see here in a straight increasing line on the log graphs. This means that as we proceed to more and more iterations, the Bayesian optimizer calculates its next point very slowly from iteration to iteration. But for SMGO, it's not much. Actually, the improvement is seen as 2 to 3 magnitudes, 2 to 3 orders of magnitude faster. So with this shown results, we can see that SMGO had a highly competitive optimization performance. And with the polynomial complexity and computational time, we can see that it offers a good trade-off between these two factors. So to wrap this up, in this presentation, we have introduced a simple global optimization approach, which is SMGO, and its mechanism. And we have also mentioned some of its properties regarding the convergence and the complexity. And lastly, comparative results are shown as well in the optimization performance, as well as the computational times. And for the next step, we are considering including the constraints and uncertainties, and of course, application to real test beds, either on the design or control of hard-to-model systems. And with that, I thank you for your attention, and I'm ready for questions. Thank you.
Okay, thank you, Lorenzo, for your presentation. Okay, maybe we have a question. If you can read in the question and answer chat, okay, you can find the question.
Oh, yes. Okay.
You have two questions.
There's a question regarding the assumption on the Lipschitz constant. Actually, this one we don't assume a known Lipschitz constant. So as we can see in the summary of the algorithm, I think we can show it here. It's an iterative procedure. So the Lipschitz constant is actually adjusted according to the existing data. So as you go on and on with the SMGO algorithm, the Lipschitz constant would actually asymptotically approach the actual Lipschitz constant, which we named gamma naught. So this one is just an estimate, but we would approach it. We would approach the real value. So at first you don't know the Lipschitz constant, but you know that it exists because of the Lipschitz assumption.
And what about the initial guess?
The initial guess, actually the initial guess, we can set it to a very small value, like 1 to the 10 to the 6. And then as we go for example the first two samples, we can already have a first estimate of the Lipschitz constant, because okay. because for a slope calculation you just need at least 2 points, and then we can just go on and on, because dense points would mean we would approach the real Lipschitz constant. Okay,
you have another question in the chat?
Yes. Okay. Based on the surrogate models, for instance, on the radial basis, have you also tried these approaches? Okay. While locally the function does not. Oh, actually, regarding the surrogate models, the surrogate models, actually regarding the global optimization with surrogate models, I think the Bayesian optimizer is also based on a surrogate model, which is based on a Gaussian basis function. So we have tried it and compared it with the SMGO. But in the stages of the design, we have of course considered the SMGO, because it's much faster it's much faster to operate on a set of cones rather than a curved model as was used in the Bayesian optimization. And then one limit of the Lipschitz approach is that the overall Lipschitz concept may be large, while locally the function.
Okay,
yes.
so sorry, Lorenzo. In order
Okay.
to stay with the schedule, okay,
Okay.
in time, you can reply the other question.
Okay, sure.
In the chat. Okay.
Okay. Yes,
okay.
yes.
Thank you very
Okay.
much. Thank you very much.
Thank you so much.
Also for your
Nice
presentation again.
Okay, thank you.
Thank you. Okay, so we can move to the next talk, which is optimizing cooperative pallet loading robots, a mixed integer approach. And Mattia Laurini is presenting the paper. Okay, thank you, Mattia. Okay.
Do you see the presentation?
Yes, yes, perfect.
Okay.
You can start. Thank you very much.
Okay, thank you, Diego, for the introduction. This is a joint work with Professors Luca Consolini and Marco Locatelli from the University of Parma, and with OCME, which is financially supporting this project. In recent years, robotic palletizing systems have become widely present in manufacturing facilities. They play an important role in efficiency, as very often the palletizing phase is a bottleneck for these plants. So having an efficient palletizing systems allows for a fast storage and delivery of goods. In literature, a lot of work has been done on the so-called pallet loading problem, which addresses the problem of placing objects on a pallet, optimizing the space usage. However, not much has been done on how to actually place these objects on the pallet. So our goal is to develop a strategy for loading the pallet in such a way that the loading time is minimized. So in general, that's the kind of palletizing system that we consider. So we have a conveyor belt that we assume it moves from left to right with one or more in-feed tracks with packages of products coming in, one or more robots that manipulate the packages, and then at the end, right before the pallet, we may have one or more stopping bars that align packages along the x-axis. In what follows, I assume that we're going to have a reference frame whose x-axis is parallel to the movement of the conveyor belt. And I also assume that the conveyor belt moves with a constant speed. Also, for the sake of presentation, I'm going to make a number of assumptions. The first one is that we consider only identical and rectangular packages. And we also assume that they get on the belt equally spaced along the x-axis. We also do not consider rotation in this presentation. And also the working areas of manipulators do not overlap. And also manipulations occur in tracking. This means that with respect to the reference frame that moves with the belt, packages only move vertically. So now, in order to explain the strategy that we developed for solving this problem, I'm going to use a very simple toy example, which has the goal of forming this very simple pallet layout made out of these three packages. Here, note that the only important thing is the y coordinate of these packages, as we assume we have a stopping bar at the end of the system, so the x coordinate doesn't really matter. The only thing that matters is the precedence between these packages. So the important thing is that these two packages have to be placed before the third one. So the first example considers a palletizing system with just one in-feed track and just one manipulator. And we modeled this problem through a variation of the traveling salesman problem, in particular, the traveling salesman problem with time windows. And here, the manipulator plays the role of the traveling salesman, and packages at their initial position and final position play the role of cities that the traveling salesman has to visit. this kind of problem can be naturally associated to graphs. So in this case, this would be the graph associated to the example I just presented. And here we have O1, which represents the initial position of the manipulator. Then we have 3 other nodes that represent the initial position of the packages. So these 3 packages here. Then we have 3 nodes that represent final positions of packages, which in this case are these opaque 3 positions. And then we have a resting position, that is the position that the manipulator reaches after it has carried out his task, which it could be, it could coincide with the origin position or just the beginning of a loop of forming other layers of the same kind. The manipulator is not allowed to travel to any node freely, but there are some constraints. And the first one is the following one. So the manipulator from its initial position is only allowed to move to an initial package position because it has to go pick up a package. Then after that, it is supposed to go drop off a package at a final position. So here's why we have edges connecting initial positions and final positions. And then once the manipulator has dropped off a package, it has to go back picking up another package from an initial position. And then once all manipulations have been carried out, it moves to its resting position. I would like to note that this subgraph given by the initial packages position and final packages position is a bipartite graph, and the manipulator keeps traveling from nodes on the left to nodes on the right and vice versa. So with the problem formulated in this way, the problem of finding an optimal manipulation sequence becomes the one of finding an optimal path that traverses the graph. And here, the edges have a cost that represents the traveling cost. It's the time that it takes the manipulator for traveling from a position to another. So in this example, the manipulator goes from its initial position to this first package and moves it to this final position, and so on. And this is represented in this way. And I would like to stress the fact that final positions do not have a fixed x coordinate. So their coordinate becomes bounded to the one of the initial position once the connecting edge has been traveled. And I also said that the traveling salesman problem variation that we exploit is the one with time windows. So in addition to what I already said, we also have time constraints on the positions because the working area of the manipulator is limited along the x-axis and the belt moves below it. So packages get into the working area at a certain given time, and then they get out from the working area after some time. So these blue and red curve represent the time windows, for instance, of the first position of the package. This one represents the second one, and this one is the third one. And this one, and this one are the time windows of the final positions. The second example that we consider, we still have one single in-feed track, but we consider 2 manipulators. And in this case, we're going to expand the model by using multiple traveling salesmen. So in this case, the graph associated to the problem becomes the following one. So we have one additional origin position for the second manipulator and one additional resting position for the second manipulator. And our goal now is to traverse the graph with the 2 manipulators that we have. and these would be the time windows. So in this example, the first manipulator visits and manipulates 2 packages and then goes to its resting position, while the second one only moves 1 package, which would be this one. And these are the time windows associated to each manipulator and the time at which each manipulator visits the packages. So this was a very simple example, but in general, we may have more in-feed tracks with the packages coming in on the conveyor belt parallel to each other. So in addition to the previous model, we need to ensure that collisions are avoided. And so we need to add some collisions avoidance constraints, because packages can only be moved vertically. So we need to guarantee that when a package from, say, position I is moved to position J, it does not collide with a package at position K. And we only want to guarantee that manipulations occur under these circumstances, where no collisions occur. So we know that from literature, the traveling salesman problem with these variations, so with multiple traveling salesmen at time windows, can be reformulated as a mixed integer linear program. And also these additional collisions constraint can be added in such a way that they are they only involve binary or linear variables. One main drawback of this approach is the combinatorial explosion of the problem as the number of packages increases. However, given the application, the number of packages is usually very limited. It usually stays below like a few tens of packages. But there are also ways for addressing this issue. The first one is that in the way we model the problem, we are solving it exactly. So this may be computationally demanding. So one could use heuristic approaches for improving the performances. And other things that I did not include in this presentation, but that we already did, is to include packages of different size. So this means that the model can handle groups of packages. So for instance, in this layout, the manipulators don't have to move singularly each and every package, but for instance, these 4 packages could be moved all together at once by a manipulator. Another thing that we can add to the model are rotations. So packages can be rotated during the manipulations. And we could also add more general manipulations. So manipulation not in tracking, but manipulations that change the X coordinate of the packages with respect to the reference frame of the conveyor belt. Another thing that can be done is to optimize the conveyor belt speed in order to maximize the production. So in the model, the conveyor belt speed is always a constant, but it could be optimized by bisection, running multiple instances of the problem. And another thing that we worked on is optimizing the package's X coordinate in such a way that the space of the occupied space by packages on the conveyor belt is minimized. And so this allows for a faster palletizing process. And also we are working on solving these problems by means of dynamic programming in order to improve performances. And this, I'm going to show you a simulation of a palletizing sequence in which we have rotations, packages coming in from multiple tracks, multiple robots, and here we also considered the grippers of the manipulators. And with this, I finish my presentation and I thank you for your attention.
Okay, thank you very much, Mattia, for your presentation. So we have time for questions. Okay. Cannot see any question in the chat.
Diego, can you hear me?
Okay, yes. Okay.
Yeah, it's Sophie, it's me. Just a quick question. So first of all, thank you for the presentation, which was very nice. I have not got if these results are already published somewhere, or you have some work in progress on that. I mean,
Yeah.
there is some reference to give to, let's say, read more about this topic.
We are working on it, and we plan to submit soon a work about it.
Okay, so this
Currently we don't have a
novel
work available on this work.
Okay, thank you very much.
Thank you.
Okay, if there are no other questions, anyway, we have to wait a little bit for the next talk in order to start at the right time. And so thank you again, Mattia, for your talk. And so I kindly ask Andrea Testa to start sharing his slides. Okay, thank you.
Okay. Can you see them?
Yes, yes. So we have just to wait about 3-4 minutes before starting. Okay, I think we can go on. So the next and last talk of this session is distributed mixed integer linear programming for task assignment in robotic networks, and is going to be presented by Andrea Testa. So please, Andrea.
So thank you for your introduction. Before proceeding, I would like to acknowledge the RC project of Smart. Indeed, this research has been done within this project. And this work is in collaboration with Professor Giuseppe Notarstefano. We are both from the University of Bologna. And today, I will show you distributed techniques to address mixed integer linear programming over network of cooperating agents with a particular focus on task assignment in robotic networks. Indeed, task assignment arises as an optimization problem in several cooperative robotic applications. As an example, we can consider a smart factory with a team of robotic agents that have to pick objects from shelves. So we may have objects which can be picked from UAV since they are in a high position, while there are objects that are on a lower position. There are objects that can be picked from both kind of robots. And in order to self-assign the task and, for example, minimize the total travel time, robots have to leverage on local computation and communication capabilities. These scenarios come with several challenges that need to be carefully taken into account. Today, I will discuss in particular the case of unreliable and time-varying communications. Indeed, if, for example, we think about Bluetooth communication among robots, then due to this criterion, we may have a link that activate or deactivate, or link may fall, so the messages go lost. And also, and this is again a particular focus of my presentation, task assignments are often expressed as mixed integer linear problems, which are well known to be NP-hard optimization problems. In this talk, I will address two different distributed frameworks. The first one is a general mean formulation, and I will show you a distributed algorithm that works under a reliable and time-varying communication network. And as an application, I will show you a multi-agent, multitask assignment. And then I will move to a generalized assignment problem for a network of heterogeneous robotic teams. I will show you a dynamic assignment servicing strategy for those contexts in which tasks are not known a priori, but arrive during time. And then I will show you results based on a ROS-based experimental platform. So the idea behind the algorithm that I will show you today is that we want a fast convergence to a good solution while having only mild assumption on the communication network. So as a first scenario, as I said, I consider a general mixed integer linear problem. So we want to minimize a cost function over a set of linear constraints when some variables are constrained as part of the variable are constrained to belong to the integer set. We consider a network of n agents communicating over a possible time-varying D graph G. Each agent knows the cost function C, but each agent is only aware only a part of the constraints of the problem. So our algorithm is based on the so-called cut-in-plane approach, which is a well-known algorithm in the centralized literature for MILPs. So what is the idea? So let's consider this two-dimensional example. Here we have that only one variable is constrained to be on the integer set, so that the feasible set is represented by these blue lines. Another set that is possible to define is the so-called convex SAL, which is the smallest convex set which include the mixed integer set. Now, if the constraints, the linear constraints of the problem describes a bounded polyhedron, then it can be shown that the convex SAL is a bounded polyhedron itself. And this is an important result, since we are going to leverage on another well-known result that states that the linear problem over the convex SAL share the same optimal cost with the original MILP. The problem is that the convex SAL is not known a priori, and in order to estimate it, it will be maybe NP-hard as well. So the idea of the cut-in-plane approach is to iteratively generate new constraints, which are called cut-in-plane, in order to approximate the convex SAL. So in our distributed settings, each agent keeps track of a candidate solution, or a candidate estimate of the solution on the MILP, which I will show you converge in finite time to the optimal solution of the problem. And associated to this variable, it's possible to define a basis, a so-called basis, which is the set of active constraints at the solution. So at each communication round, the agent generates two different kinds of cutting planes. The first one, which is depicted here, is the so-called Gomori cut. So it is possible to see that these constraints actually cut off the current estimate while preserving the mixed integer set. The other one is called cost-based cut, which we have shown to be necessary in order to have finite time convergence. And it's not depicted here for the sake of clarity, but it's actually a constraint which is based on the cost function and on the current estimate of the optimal cost. At this point, agents gather the basis from its neighbors, and then it constructs a linear problem which is based on the intersection of the basis and on its current and on its local data of the global optimization problem. It solves this linear problem, so this is easy to do since it's a small linear problem based only on a few active constraints, and it updates the local estimate with its basis, and then it shares again the basis with its neighbors. What we have shown is that under the assumption of jointly strongly connected D-graph bounded the initial feasible set and integer optimal cost, then in finite time agents reach consensus on an optimal solution of the problem. Then we extended this result to the case of general and MILP, where we removed the assumption of integer optimal cost and we propose a distributed algorithm then, since still in a finite time, converge to an approximate solution, feasible solution, which differs at most epsilon in cost from the real optimal one. The assumption of jointly strongly connected D-graph, as I will show you in the next slide, models not only the fact that the communication may be time varying and directed, but also unreliable. Indeed, as a motivation example, we consider a multi-agent multitask assignment problem where we have a set of vehicles here represented by triangles that need to serve a set of tasks here represented by diamonds. So agent compute offline, each vehicle's compute offline, a set of feasible paths that connect the vehicles to the tasks. We want to serve all the tasks, and in the optimization scenario, we consider also smart agents that are scattered in the environment and are aware only of the constraints related to path in a certain neighbors. So here you can see the result of an example with 30 vehicles, 32 tasks, and more than 70 possible paths, with a network subject to packet loss from 0, which is the case of ideal network, to 70% of packet loss. And you can see that they fastly converge to an optimal solution of the problem, to a feasible solution of the problem, which differs just 0.1 from the optimal one. As a second scenario, as I said, I will address generalized assignment for multi-robot systems. So we have a network of n heterogeneous mobile robots that communicates again over a D-graph GT, possible time varying. We have n tasks to be serviced, and in this case, each robot knows a local contribution on the cost function CI, which may be a reward if the agent performs a certain task or not, or maybe a penalty on the total travel distance. And also each robot knows the set PI, which is a knapsack constraint, which somehow limits the amount of tasks and the kind of task that the robot can perform. What we do is to propose a distributed algorithm based on the idea of the branch and price approach. So how does the branch and price approach works? First, we exploit, the algorithm exploits an equivalent reformulation, where Zi is expressed as the combination of the vertices of the convex hull of PI. Now, since in PI we have integrality constraints, this combination must be subject to integrality constraint as well. So the combiners of the vertices of the convex hull are integer as well. This results in another optimization problem, which has a large number of variables. The matrix V is a large matrix. Variables are supposed to be integer, so this is still hard to solve, but there's a special structure that I will show you in a while how to exploit. So as a second step, the branch and price solve a sequence of relaxed problems. So the variable is now continuous, and this becomes linear problems. Problems are solved by means of column generation. I will show you in a while what I mean by column generation. And since we have this sequence of problems, they can be represented as a so-called branching tree. So we have constraints that are more and more constrained. Here, as an example, the problem MPL plus 1 inherits the same constraint of MPL and it has an additional constraint. The idea is that adding constraint on the Z variable results in a smaller matrix B, meaning that these problems are smaller and smaller, so they are easier to solve. Finally, the algorithm keeps track of incumbent variable J-inc and Z-inc that keeps track of the best optimal solution and cost found so far during the exploration of the tree. So for each solution of a problem, for the solution of each problem of the tree, the algorithm checks if the solution is currently improved the local incumbent, and if it is also integer, then the incumbent is updated. Otherwise, if the cost seems to be improving the incumbent, but the optimal solution of the problem is not integer, since I repeat that this is a linear problem, then it has two new problem constraints by adding two new problems to the tree by adding constraints. And otherwise, if the cost is not improving, then what is done is so-called pruning. So simply the algorithm go on and extract a new problem from the tree. In our distributed scheme, each agent has a local tree and has local incumbent ZI of t and ZI of t at time t. Agents cooperatively explore the local tree, and we assume that they have some common rules to perform the incumbent update and branching. So what happens at each communication round? Similar to the previous case, even though here the bases have a different geometrical interpretation, agent get their basis from the neighbors. At this point, it constructs a linear program, which is called a restricted master problem. Here it's called restricted because it is based on a linear problem with a smaller matrix vi with respect to the entire V. It evaluated a basis of the optimal problem, and then through a so-called pricing problem, it tried to gather some information from V into the evaluated basis. This is done by solving a pricing problem, so the generation of a new column. Even though this is a mixed integer linear program, since here we have integrality constraints, this can be done efficiently to dynamic programming. And then, if it is possible, it includes the column into the new basis by means of a so-called pivoting operation, and then it broadcasts the basis to its neighbors. We show that in finite time, agents converge under the assumption of L strongly connected digraph and non-empty feasible set. This assumption can actually be relaxed to an optimal solution of the problem in a finite number of iterations. And actually, there are two main pros of this algorithm. There are the fact that, okay, we have finite time convergence, and the L strongly connected assumption assures us that it works under asynchronous and time-varying communication. So this algorithm can be really implemented on a network of robots, or real robots, and indeed, what we have done is to consider a scenario, a distributed dynamic assignment service in strategy scenario in which we have a team of heterogeneous robots. We have a set of tasks which are scattered in the environment. Tasks are not known a priori, but arrive during time, and we want to minimize the total mission time. So here we have an example of scenario from the perspective of the robot, of the generic robot. So we start with a set of known tasks and we formalize the optimization problem. At this point, we evaluate an optimal allocation, and the planner of the robots evaluate the shortest path connecting the robots to the assigned task, and then the actuation starts. What happens if a new task arrives? A new optimization problem is considered with the new available data while discarding the data related to tasks already serviced. Again, there is an optimization, a new reallocation, and a new path planning and actuation. What may happen is that during the optimization, a new task arrives. In this case, the previous optimization is interrupted, the problem data is updated, and so the procedure restarts. In order to implement this on a real network of robots, we implemented a ROS platform, which has the main advantage that does not need a central computation unit, so that the computation can be really distributed over a network. We can test the algorithm over a real network. In particular, we done it through Wi-Fi communication, and thanks to ROS, it's easy to handle heterogeneous teams of robots. So in this case, UAVs and ground robots. There are two main layers in the architecture. The first one is optimization layer, when we have optimization ROS nodes that represent the generic agent and that communicate with other agents in the network. In this case, we also consider access to a non-cloud resources, as an example, a shared memory, but I would like to stress out that it is not needed from a theoretical point of view, but is done in practical application to enlighten the memory required from the agents. And then we have a control layer which receives tasks from the optimization node. It dynamically handles path planning. So if new allocation arrives during the actuation, and it actuates the robot. So to conclude, in this talk, I presented distributed method for mixed integer linear program with application to task assignment problem in cooperative robotics, and I will show you an experimental platform. So thank you for your attention. And since I am out of time, during the question, I would like, if possible, to show you a short video from the experiment. Thank you again.
Okay, thank you very much, Andrea. You can run the video. Okay, so while we wait for possible questions. Okay. If you want, you can comment on.
Sorry, I'm not able to see the question actually.
No, I'm
you mean
thinking about the video.
Yes, sorry.
Yeah.
So yes, here we have an example with 5 vehicles, and in particular 3 UAVs and 2 ground robots. We have a set of initial 10 tasks. So what we are done here, vehicles are actually optimizing. And so here they found the first allocation, then new task arrived. And here it is possible to see how the planning actually changed in order to consider the new tasks. So while moving, they change their local actuation. And so this is done until no more tasks, in this case, no more tasks are discovered, otherwise the algorithm continues to allocate and dynamically re-optimize the problem.
Okay. So it seems that there are no questions. So thank you very much again, Andrea, for your talk. I would like to thank you all the speakers for their really interesting presentation. And I would like to remind you that at 11, you can meet all the other colleagues for the virtual coffee break in the virtual squares that you can reach through the Zoom link available on the conference website. And I would like also to remind you that the next session will start at 11:30. Okay, so if there are no questions, I think we can end this session. Thank you again to everybody also for attending.